Hello guys, this is Professor AutoCAD here. Today we'll be talking about black holes. First of all, let's study the proposal of black holes. Who proposed black holes? The first person was actually Einstein, but he thought that the concept that explains black hole was so radical. In fact, he had strong misgivings. Einstein concluded in a 1939 paper in the Annals of Mathematics that the idea was not convincing and the phenomena did not exist in the real world. But still, Einstein formulated the equations for the gravitational field in his general relativity. The general relativity is really a powerful tool for us to study the universe. Later, there was a man named Schwarzschild. The Lorax, is that you? Okay, so Schwarzschild, he obtained a solution by solving the gravitational field equation in Einstein's general relativity, but he found that the solution of this equation is very strange and has many wonderful properties. So he called the solution a black hole. He said that there may be such a strange celestial body in the universe, but people don't know whether if there is one. So let's go find it. Well, Stephen Hawking made a few more attempts among the solution. He introduced the quantum field theory on top of Einstein's general relativity. Through the analysis of quantum field theory, Hawking has made detailed descriptions of the nature of black holes. But so far, these theories are still speculations. That is to say, whether black holes exist or not. People were still in the stage of doubt back then. This is why Hawking has not received the Nobel Prize until now, where the first image of the black hole was released in 2019, 1 year after Stephen Hawking died. So, what are the properties of black holes? Let's talk about the basic nature of a black hole. Is that its mass is so large that even light cannot escape. Light cannot escape. In order to understand the escape, let's start with a more classic example. So, this is the Earth. Newton once said that if you launch a cannonball at a very tall mountain, it will fall back to the ground if the speed is relatively slow. But if the speed reaches a certain value, it will not land, but will circle around Earth. This speed is called the first cosmic velocity, or the orbital velocity, around 7.9 kilometers per second. And if the speed continues to increase, well, how much should it increase? What will happen to it if it increases to 11.2 kilometers per second? The cannonball will never return to Earth and escape to the infinity and beyond. We call this the escape velocity. Great. In classical physics, the escape velocity v2 equals to the square root of 2gm over r, where m is the mass of the planet, r is the radius of the planet, and g is the gravitational constant. We will find out that when the mass of the planet gets bigger and bigger and the radius of the planet gets smaller and smaller, then the escape velocity v2 will increase. We know that the fastest speed in the universe is the speed of light. If even light cannot escape, then nothing can escape. So we can use the speed of light, c equals to square root of 2gm over r, to get the radius of the planet at this time. Well, r equals to 2gm over c squared. Then this is called the Schwarzschild radius, where if the radius of the planet is smaller than this value, even light cannot escape. But we should note that this process is actually an analogy process. This equation is obtained from the general relativity. Although we look at it like this, and it seems to be almost the same as the original equation for the one for v2, in fact, its meaning is slightly different. We got it by analogy. If we take the mass of the Earth, what is the mass of the Earth? It's around like 6 times 10 to the power 24 kg, right? If we bring this number in, we will find that the Schwarzschild radius of the Earth is 0.01 meters. Therefore, when the radius of the Earth is 1 centimeter, the Earth will become a black hole. So what are the properties of black holes? One such thing in the nature of black holes is the curvature of space-time. We know that a large object bends space-time. The curvature of space-time is not that easy to understand. Let's use a simple example to illustrate. If there's a celestial body M with a very strong gravitational force, where we assume this is a black hole, and there is a circle outside. This circle is called the event horizon. What does the event horizon mean? Well, when a person A gradually approaches the event horizon, he still has the chance to escape from the black hole. But once A enters the event horizon, even if his speed is the speed of light, he can no longer escape from the black hole. In the end, A must hit the center of the black hole. This center point is called the singularity. When A is moving forward at a certain speed and there is a person B nearby observing A, what will B see? A thinks that he's moving in a straight line at a uniform speed, but B thinks that A is getting slower and slower. And finally, when A is infinitely close to the singularity, B finds that A is no longer moving. This is the time slowing effect caused by gravity. Do you still remember the movie Interstellar? Romilly stayed in the Endurance, and the others went on to Gargantua. It turned out that 23 years, 4 months, and 8 days had passed on the Endurance, but to Cooper and Brand, it was only 3 hours and 17 minutes. Why? This is because time had slowed down. So black holes' first effect is that time slows down. Time slows down as you get closer to the black hole. So what happens if you go inside a black hole? Once you enter the black hole, you will never come out again, because even when you are at the speed of light, you can't even get out, let alone using slow spaceships. Moreover, due to the strong bending of space-time, space and time will be exchanged. We know that outside the black hole, time is unidirectional and space is bidirectional. Unidirectional time means that you cannot go back to the past, you can only go towards the future. And bidirectional space means that you can go forwards and backwards on one dimension. But after entering the black hole, it means that time becomes bidirectional and you can go back in time. But space is unidirectional. You can't go back. You can't turn your head and walk away. The only place you can go towards is the singularity. And in the process of moving, you will eventually die due to the strong gravitational field of the mass. This is definitely a more bizarre feature of the black hole theory. We also observed such situation in Interstellar. Cooper dropped into a black hole, and in the future he dropped into a black hole and travelled back in time and saw his daughter in the past and gave her some hints and notes. I'm not going to do spoilers if you haven't watched the movies. Well, that's probably all for today. If you like my channel, please accent the like button, follow my Instagram account, subscribe and turn on the notification bell. And I'll see you Beaverfix next time. Bye!